fellas. Welcome to our brand new lecture series, Cryptogue Talks by NP Club. So thank you very much for waiting and apologies for delay. So I think we are good to go. So yeah, this is our brand new lecture series on the topic of cryptography, obviously, that's why you are all here. And we'll essentially try to cover the math involved in cryptography, so you actually accessibly try to approach it in a new manner. So obviously there will be no prerequisites. The lecture format will be as follows. We will first cover the mathematical prerequisites required for today's lecture in the first 40 minutes or so, and then we'll move on to the cryptography part of it, where we'll actually explore the cryptographic aspects of how use number theory, group theory, algebra, and so on to actually use ciphers and various other cryptographic aspects, and then go on to even apply them in a further application session. That's going to be a hands-on programming session, right? So, alright, on that note, I'll be happy to welcome our first speaker for today, who is Nirav Bhattad. So, give it up, my guys.
So, one small correction, this talk is in collaboration with cyber security community as well. Yeah, so, since we don't assume any prerequisites, I'll be walking over the basics of modular arithmetic, and then Mehul will start with fields and finite fields. So the motivation for modular arithmetic is like, suppose you're working in the 24-hour format and then you're converting to a 12-hour format. Then you're basically taking the hour modulo 12. 1300 hours is 1 p.m., which is one module. So yeah, that is how we define modular arithmetic. So we write it as so we define A is congruent to B mod n. So basically, you can also think of it this way as A and B leave the same remainders when you divide it by n. Then, so for example, 13 is congruent to 1 mod 12. And when you take modulo certain class, then you get these structures called residue classes, which are each residue class gives the number, like the set, which leaves the same remainder when you divide it by m. So when you suppose you are taking modulo 12, then you get 12 modulo classes, 1 bar, 2 bar, 12 bar. I mean 0 bar, 1 bar till 11 bar. And then 1 bar is just 1, 30, 25, and also the negative ones as well. Then now modular arithmetic has some special properties, where, like if you have A congruent to B mod n and C is congruent to D mod n, then A plus C is congruent to B plus D. A times C is congruent to BD mod n, and A to the power of n is congruent to B to the power of n mod n for every n. Yeah, so does anyone have any doubts with the definitions of these basic properties?
So these are the rules we have to follow. These are just the rules that are there.
No, like
They can be proved.
the only definition is A is congruent to B mod n when m divides A minus B.
Yes.
And these are the three properties which you can derive. I'm not going over the proofs because we don't have time, but these are some properties. Then, there's this one nice. Those are the residue classes when you consider, like when you are considering mod m. So, like, it is basically a set of elements which leave the same remainder when you divide it by m. Yeah. So there's this one nice result which you get, is that if you have a polynomial with integer coefficients and a and b are two different integers, then a minus b divided f of a minus f of b. This is used a lot, and you can derive this easily using modular arithmetic when you consider mod a minus b.
What is f?
Sorry.
What is f?
F is any integer polynomial. Polynomial with integer coefficient.
Can you explain for example
For this property here, I mean, we have like a polynomial f of x. And suppose you take a is equals to 5, b equals to 2, then 3 divide whatever. And just take, you can check it. Yeah. Yeah, okay. Now I'll just go over the Euclidean algorithm. Everyone would have done it, but still. So Euclidean algorithm is basically used to find the greatest common divisor of two integers. So suppose you have to find GCD of a comma, and you basically proceed in this fashion where a is equals to continue like this till you basically get the remainder term over here. So you get something like Rn minus 1 is equal to Rn times.
Can everyone hear him? Mike,
And why I'm writing this is because it is also used to find modular inverses. So I'll come to modular inverses in a bit. So basically, there's this lemma called Redruth's lemma. It says that if C is the GCD of a comma b, then there exists integers x comma y such that ax plus by is equal to c. And to find the integers x comma y, we use the Euclidean algorithm in reverse. So I'll demonstrate that in right now. So suppose suppose a is equals to 21, b is equals to 12, and we have to find integers x and y. So we first proceed using the we first apply the Euclidean algorithm. So we get 21 is equals to that the GCD is 3, and now we go in reverse. So basically we write 3 as 12 minus 9, 12 minus 1 into 9. Then we replace this 9 with 21 minus 12. So it's equals to 12 minus. So basically we get that a is minus 1 and b is 2. And now basically since we have Redruth's lemma now, we can basically find inverses, modular inverses. So basically a modular inverse is defined as if you have an integer a, then modular inverse of A is defined as an integer x such that ax is congruent to 1 mod n. And now we can do two things with this. One, we claim that modular inverse of A mod n exists only when A and M are co-prime, because then if they are not co-prime, then basically the GCD C would not be 1. It would be greater than 1, and then we won't be able to get the 1 over here. Like, the way we find modular inverse would be like we find the integers ax plus by is equals to 1 because the GCD is 1, and then when we take this and when we reduce this equality modulo m, we get that ax is congruent to But then if the GCD of A and M is not 1, then there will be something like some other integer over here. Then when you reduce it modulo m, you won't get 1 over here. So the condition for modular inverses to exist is that A and M should be co-prime. And with this we can also state that if we take M as a prime, then every integer which is co-prime to A every integer less than P will have a modular inverse because it is co-prime to the prime, co-prime with P. Okay. Anyone has any doubts with this?
Ax plus my is equal to that.
Yeah, so suppose we choose we apply Bezo's lemma on A and M. There exists integers x and y such that ax plus my is equals to the GCD, and we are choosing A and M such that they are co-prime. Co-prime means that their GCD is 1.
We are assuming or we are choosing them like that?
No, it is necessary for them to be co-prime to find a mod. And then when we reduce it mod m, we get this equal. It is congruent. Moving on. We'll talk about bit strings. So bit strings are basically strings which are made up of 2 characters, 0 and 1. And then we can define various operations like AND or XOR, XNOR, whatever, like all those operations. And the most important operation for cryptography is XOR. So just revising what XOR is, suppose you have 2 bit strings. What is the XOR of these 2? Sorry?
0, 1, 0, 1.
So you can see XOR as basically adding them and taking modulo 2. Like adding 0 and 1 taking mod 2, adding 0, 0 taking mod 2, like adding 1 and 1 and then the addition is 2, but then you take mod 2, so you get 0. Like this is another way to look at XOR. And you can also...
There is no carryover, right?
No, because you are considering mod 2, it will always become 0 or 1. And yeah, so if you can also look at it as a field of 2 elements 0, 1. Now Mehul will start with what a field is.
So hello guys, I am Mehul Borad and I am going to be continuing from where Nirav left off. I'm going to tell you about fields, finite fields, and how it's going to be used is going to be covered by Nilabha and other people. So I'm just going to give you the background necessary so that you can actually understand and work on what they are going to teach later. Alright? So right. So what is a field? So like how many of you have heard the word field in the mathematics sense, not in the English sense? 1, Almost no one. 2, 3, 4. Right, very few people. Alright. So, a field is a structure, it's a mathematical structure with some properties. So, like very common examples of fields would be the real numbers, the complex numbers, even rational numbers are fields. So, but it requires some property. So, I'll just list them down. So, a field first must have a collection of objects that we are working on. So, that we generally denote as F. And then two operations, addition and multiplication. Alright, so these need to satisfy some. Is this audible? Is that alright? Okay, so this needs to satisfy some properties. I'll just list them down. So, first of all, addition. First property is closure. So, A plus B must be in the field A times B. So, A, let's just write as a dot. Dot is just less of a hassle to draw. A times B also belongs to field. Alright, for every pair A and B in the field, A plus B must be in the field and A times B must be in the field. Alright, it's closure. Number 2 is associativity, which just means that A plus B plus C is equal to A plus B plus C. Like very normal property that you would expect for multiplication and addition if you were to generalize them. Alright, these are for all pairs ABC. Number 3 is commutativity. So A plus B is B plus A. Alright. Fourth property that is required is inverse. So basically we must have the additive inverse. So we must have the negative element. So for all A that belongs to the field, there exists A inverse such that A plus minus A such that A plus minus A is equal to, okay, I need to first define what 0 and 1 are. Oh, okay. Fine. Till now is it fine or should I write stuff again? Just continue. Understood, right? Fine. So, fourth is identity. Basically, there should exist something like a 0 and something like a 1 in the field. So, there exists 0, 1 in the field such that 0 plus A is equal to A and 1 times A is equal to A for all A in the field. Alright? Fifth property is that inverse. So basically you should be able to subtract and you should be able to divide everything except 0. So for all A belongs to the field, there it is. the additive identity, and for all A belongs to C without 0. So except for 0, everything should have multiplicative inverse. Does this make sense? There's another property which really defines what the relation between addition and multiplication is. So that is that it is multiplication is distributed over addition. So distributivity so basically A times B plus C is equal to A times B plus A. So all of these seem very natural properties, right? Like what you would expect of real numbers, complex numbers, and so on. Even rational numbers do satisfy this, just check it. But integers don't. Can someone tell me why integers don't form a field?
Inverse. Multiplicative inverse.
Yes, so of course there is no multiplicative inverse for 2. There would have to be one value, right? That's how you would form the rationals. Alright, so those would be like the generic examples of fields. Now for a somewhat weird example of field. So like Nirav had told Z over PZ, or basically the modulo the modulo classes for any prime P. Given a prime P, the modulo classes, those form a field. That might be a little surprising, but this is true. Actually, I can just
Next page.
Undo.
Bottom right, next page.
Bottom right. 1 second. Excuse me.
Mehul, bottom right, next page.
Yes. Right. So what Nirav had described, right? So the classes 0, 1, so on till m minus 1. These modulo classes. So basically, it is a set of all numbers that give 0 as a remainder. So 0, m, 2, and so on. Right. So consider this set of objects under mod m. Under this doesn't always form a field. As Nirav had told that there doesn't always exist a multiplicative inverse. Isn't that right? So like he had told that only if A is co-prime to M, does there exist multiplicative inverse within this itself. Right. So for all of these elements to have a multiplicative inverse, what should M be? Prime. Exactly. So prime really come up a lot in discrete math, a lot in like finite stuff, finite structures. They come everywhere. Groups, fields, everywhere. So we can see that only if we consider these set of objects, so 0, 1, so on till p minus 1, that p is a prime, under mod p, can this be a field? And this actually turns out to be a field. You can check this out. I don't think it's too difficult, like all of these properties, because addition modulo m, multiplication modulo m, all of that is very natural, right? Only unnatural thing would be the division. Even subtraction is not so bad here. So like if I have some number m belongs to this, m plus p minus m must be, except if m is 0, m plus p minus m must be congruent to 0 mod p, right? So p minus m would be the additive inverse. For the multiplicative inverse, you would actually have to do the Euclidean algorithm, right? You have to actually find out. So let's suppose m and p. We know that p is a prime, so m comma p GCD is 1. So from the Bhattad's lemma, there exists x and y such that this happens And if you write this equation modulo p, what happens? You'll get mx is equal to 1. Right, so x would be what? Multiplicative rule. Yes, exactly. And we have an algorithm to find x, right? We go through the we go through the implementation algorithm to find x. Does that make sense? Makes sense? Yeah. Nice. Alright. So this forms a field, and this is a finite field, you can see this, right? So finite fields are a little weird in this sense. Now, as it turns out, if you consider finite field in this form, where you're talking about modulus, as I just showed, it can only be of prime cardinality, right? You can only have prime number of elements in this. As it turns out, any finite field, so any kind of structure whatsoever that satisfies those properties, right? Any finite field must have cardinality of p power k. So any finite field can either have prime number of elements, or the number of elements is a power of a prime. That was a tongue twister. Does that make sense? Okay, I didn't actually show why that is the case, and I'm not going to go into that. So just take it given for now. I'm going to show you an explicit construction for the finite field of p power k. Also, as it turns out, not only does the cardinality have to be p power k, but every such field which is of the same cardinality, which has the same number of elements, is basically the same field. So like you cannot really have two different fields that have the same cardinality. And what does it mean to be the same field? Is basically there must be isomorphism. And I'm going to explain isomorphism. Before that, I'm going to get into what is explicit. I guess it might be better for me to go into isomorphism before I get into that. So isomorphism also is an interesting or an important thing. Okay. So here isomorphism just means intuitively isomorphism between two fields or structure fields. It just means that you have a one-to-one mapping, you have a bijective mapping between the elements of first and the elements of second, so that the structure is preserved. Right, so you can actually kind of like write down any equation, any equality, any property, replace all of the occurrences of the first field with the corresponding elements of the second field, and that still holds. Does that make sense? So basically what this means is, if I have field 1, addition 1, multiplication 1, and if I have field 2, addition 2, multiplication 2, then so basically a plus b. So okay, there exists a bijection, just for that phi, such that these properties are preserved. It's a bijection from f1 to f2. So phi is a bijection from f1 to f2. Not only that, but phi of a plus b is a1, okay, a comma b, where a and b is in f1, is equal to phi of a plus 2 of phi of b, and also phi of a. So 1 and 2, so there is two different fields.
Plus 1 and plus 2 are addition and multiplication for two different fields.
Yes.
Okay.
Does that make sense? Is it confusing? Because like think of them less as addition and multiplication. Think of them as operations, right? Like they behave like addition and multiplication in some ways, right? But think of them as actually operations on like a abstract structure. right? In fact, I could even have some kind of structure where I'm talking about like all kinds of rotations of a cube or something, you know. I can have any kind of structure that may not be a field, but all of these kinds of structures can be described by some kind of operation and some kind of set of elements, right? That's why I've written them down like this. Okay, does that make sense? Any doubts till now? Confusing, understanding? Batao? Nothing?
What is the last
This one?
What are you trying to
So basically what I'm saying is that I have this bijection from elements of field 1. Field 1, field 2. Right. I have A here, I have B here, I have A plus B here. Right. I have corresponding, let's call it A tilde, B tilde, and I have A plus B, A tilde plus B tilde. Now I have this bijection phi. A goes to A tilde. Well, basically that's what the tildes are. Right. So my phi takes A to A tilde, B to B tilde. A plus B is this is A plus B from taken from A plus A and B. What this equation is telling that if this is basically let's just call this A tilde, let's call this B tilde. So if A plus B is this element, then phi must also take this to this. Does it make sense? Like addition is preserved under this transformation. So like I first add my elements, then translate the same as first I translate them, then I add them. Make sense? So I first add, then translate is the same as translate both, then add. Does that make sense? So basically this means कि you have any expression, like you have any identity like A plus B is equal to C, you know, anything like this. Anything like this, right? I can apply phi both sides. And after simplifying, what would this imply? This would imply phi of A plus phi of B equals phi of C. Right, it's like each individual element I'm taking a phi. Isomorphism, yes. So isomorphism is a special kind of bijection between two fields. Does that make sense? It preserves addition, it also preserves multiplication. So this is also true. Phi A dot 2 phi of B. Alright? Alright?
Mehul.
Okay. In the bottom part, the plus and the first, like phi A plus B, the A plus B should be plus 1 and the below it should be 2, right?
Yes, you're right. We need to separate what they mean.
Every field must define an equality operator to it.
Define an equality operator. No, because you're kind of saying what equality means here, right?
From there only.
Did I not define? Oh, yes. So I am already saying these things. This is equal to this. So that is kind of how I'm defining my equality operator, if you want to call it that. Does that make sense? So like I'm saying that A times B is equal to B times A. That is one property of my equality operator, if you want to call it that.
But suppose I define equality operator to be like irrespective of what is on RHS and RHS is always true. So then even integers would form a field, right? Like if equality always returns true, irrespective of what is on the left hand.
You really shouldn't think of equality as an operator really. A, so something on the left is equal to something on the right. Only if there is the same element in the field. Does that make sense? Like that view, I was trying to go with your view and tell you that these are the properties that the equality operator satisfies. But in general, that's not a very common view to have. So for you to like, it's probably better for you to just think of this equality as only if the two are exactly the same element in the field. Not as a kind of like an equivalence relation, general equivalence relation. No. It's the what do you call it? It is only true if both are exactly the same element in the field. Does that make sense? So yeah. Anything else? Any other doubt? Right. So this, and with these two properties, you say that the fields are isomorphic. Alright? Does that make sense? Like just with this you can say a lot actually. You can say that if you take phi and then A inverse as the same as just take phi then inverse. Almost everything you can just change. You can basically write an equation and replace all of the elements with the corresponding element to the other one, and the relation must be true. That's the meaning of isomorphism. I mean, the formal definition is like this. I just told you. The intuition is basically they behave the same way. Like you're just renaming the element. Does that make sense? So I can define my modular to be 1, 2.
Meaning is same, interpretation is different.
Yes. Interpretation is. What do you mean by interpretation?
And like the way they think is different, but what they are understanding is the same.
I'm confused. I'm not sure I understand you. But I can do this, right? So Nirav had chosen 0 to m minus 1 as the elements for the modular. I can choose anything to represent those. Right? I can be 1, 2, I can be 1, 4, I can be alpha, beta, I don't give I don't. It can be anything. Right? So basically that's what it's saying. You are basically renaming the elements. The structure is the same. Properties is the same. All the equations are the same. That makes sense? That's isomorphism. It's like just a fancy name for a very simple thing. It's a renaming. So we get into what Galois fields are. Basically, Galois fields are just finite fields. So another fancy name for a very simple thing, at least definition wise. So Galois fields are just finite fields. That's it. Literally that's the definition. So for finite fields. Yes. So basically that means ki F here is finite. There are finite number of elements. So we saw some examples, right? That were PZ. Modular. Residue class. We saw the example. Residue classes, modular,
Number of
prime.
elements. One second. Number of elements in the residual class or the number of residual classes itself?
No, the number of residue classes. So you actually do not even define it like that per se. You just go with, okay, I have f as 0, 1 till p minus 1. That's actually my definition of f. And I'm defining addition a little differently. Almost the same thing, but if it crosses p, then I subtract p.
Okay.
Multiplication, kind of the same thing, but I just take out the remainder. I'm defining them a little differently. Does that make sense? Yes. So all of those have finite number of elements. That's why they call it finite fields. So because there is so much structure in this, there is so much to be followed by the field, right? I showed you so many properties, right? Because of that, there are actually very few ways to get different fields. In fact, I told you, right? So every finite field with the same cardinality is isomorphic to each other. Basically, they are the same field. So there's only one field with one finite cardinality.
Yeah.
And in fact, the cardinalities must be p power k. For any prime p. This is true. I'm not going to prove it. You can look at the resources for that. Alright?
Can you repeat the last part? Like p power k is required for what?
So it turns out that the possible cardinalities, the possible sizes of my field is a prime power.
Okay.
Does that make sense? So I already told you that for the modular arithmetic case, like when you're in residue classes, you couldn't have any residue class. You could only have it modulo prime. Make sense? Now, if you consider even more general structures, you are like, let there be any kind of structure that satisfies these properties. It doesn't have to be looking like a residue class. It turns out the number of elements must be p power k. That's it. Okay? Fine. So let me actually get into the construction of p power the p power k field is. Like there's only one field, but there are many different realizations of the field. Like there are many kinds of ways you can represent the same field. I told you, right? Both are just isomorphic. We have different representations of the same field. Sometimes it's not so obvious how the isomorphisms are, but they are there. So for k is equal to 1, we know we know a way to get a field, right? It's just the residue classes, right? So for bigger case, what you can do is actually you can look at for this actually called n. For bigger n, you can actually look at polynomials in the fp actually in the standard notation f subscript p or Galois field gf of p is the notation for the field with 3 elements. The Galois field with 3 elements, both the same thing. So for this, what I am talking about right now is f of p power k or Galois field of p power k. Okay. Now let's look at, for this, what I do is I look at all polynomials with degree at most n. And all polynomials in x. So I have p of x. I look at all polynomials in x. a0 plus a1 x plus a n minus 1 x power n minus 1, like this, where a n minus 1 could be 0, right? So degree is just less than n, it could be lesser than n minus 1 also, okay? And these a0, a1, an, so on, are actually part of fp. Does that make sense? So they are actually part of fp. So you do the addition, multiplication.
Px is just a polynomial.
It's a polynomial.
Just a polynomial. It doesn't have some relation with the fp.
No, it does. So the coefficients of polynomial are members of fp.
The polynomial itself is a member of fp to the power n. Is that what you're saying?
You could say that, but then I'm not sure how you define operations properly. Like fp power, like there is the specific way I think you say a field square operations happen. I don't think that's how it happens here. So like a comma b into c comma d is not equal to a into c comma b related to this. Right. That makes sense. Okay. So all of these coefficients are from FP. Basically, they are from 0 to P minus 1. That's what I'm saying. And also, they are acting as the residue classes that I told earlier. Na? So, they are from FP. So, I can add an element in this. I can multiply, I can divide as well to get in this. Does that make sense? No, it's not by, it's or. Both are the same thing. Just different ways of calling the same thing. Where are you? So an example of this would be if I'm just taking 3 square. So a member of F3 square, which is just 9. F3 square, a member of this would look like P of x is equal to 2 plus 1 x. So 2 plus x. But not 2 plus x square. Does it make sense? Now I will define addition and multiplication. Addition is very simple. So px plus qx. So px and qx are elements of f of pk. Okay. Px plus, so no, actually if you actually call it p plus q of x is actually just p of x plus q of x mod p. Matlab basically you are adding this where this addition is mod p. That's what I was telling earlier, right? So b0 plus b1 x plus so on. When I'm adding these two, I add these two. If it exceeds p, I subtract p. I'm doing this modulo addition modulo p. Basically, just parallel addition modulo p. Right? Doing what we did last, but like n times. Okay? Huh?
How did you write
And that's an example.
And like how did you write?
How did I? Huh?
2x plus 1 was
Yes. 0 is also an example, 1 is also an example, 1 plus 2x is also an example. Does that make sense? All of those. So can you tell me how many elements are actually there in FPK then from this definition?
number of elements of
FPK, where each element is like this, and each of them is from 0 to p1 x1.
infinite.
P and n are fixed.
It is finite.
I mean, it's just how many possibilities are there? P,
P1
P is
will not have to be different. P1 will not have to be different.
no different. It doesn't.
I thought it was the same as
Can we have that discussion later?
He can't be safe. Even cannot be good to you.
मतलब we will say that these two are equal if only all the coefficients are equal mod p. So अगर suppose हमने p और n fix कर दिया, suppose p 3 and 2 है, we will say that the two polynomials are the same element in f3 square if all of the coefficients are same modulo p. या अगर मेरे पास एक element 2 plus x or 3 plus x, these are different because coefficient is available. But if I have 2 plus x and I have 2 plus 4x, is a big sum.
Plus 4.
These are same.
This is 2 plus 4.
You see 1 and 4 are the same mod.
Yeah. 2 plus x, right? Plus 4x. Mod field दोनों का
Alright, so okay, so time has taken hold. So like I have to conclude the discussion, but I was about to get to the interesting part of multiplication. Addition is simple. I'll just tell quickly and then we'll conclude everything. In multiplication, what you do is actually you look at an irreducible polynomial of degree n. So how would you normally multiply two polynomials and take, like, if you were to just think of multiplying two polynomials like this, you would have to degree 2n minus 2 at most, right? You want to actually kind of like reduce that degree, right? Think about how generally you reduce degree with like remainder. Taking a remainder with polynomial is how you reduce degree. You might take the x power, I'll take remainder with x power n, so I'll just forget everything after n. That's one way to do things. But actually, that's not a very good way to do things. You can, if you take remainder with a irreducible polynomial of degree n, it turns out that your field properties are preserved. So you can actually take multiplicative inverse, which is due to Euclidean algorithm applied again. So just think about this. If you define multiplication as just multiply these two polynomials normally, then do remainder a polynomial which is irreducible. So like some special polynomial, I call it lambda of x. This special polynomial, I take remainder with respect to this. This is of degree n. I take remainder with respect to this. This is how I define multiplication as. Now if I define it like this, I can actually take inverse, like an inverse polynomial that exists. You can get this with Euclidean algorithm again.
What do you mean by irreducible polynomial?
So basically you cannot write it in factors. You cannot factorize it. Okay? Irreducible over fp, not normal. Okay? Let's just try to conclude the discussion. So what did we do? We have learned what a field is. We have learned the definition of a field. It has all these properties, right? Some very common properties. You can basically do division, addition, multiplication, subtraction. Division without this not good. Alright. We saw a very simple, a very simple example of a field. So the simplest example of a finite field really is like Z2, which Nirav had shown, like addition modular XOR all the things. Right. So another simplest example, like you just have two elements 0, 1. It's very simple to make a field out of this. Then we saw how to generalize it to prime. Then the people are K. It has these sets of polynomials.
What's the answer? Like, how many number of fields that can be possible?
How many number of elements, not fields, elements. So if I define it like this, so 0 to b minus 1, this can be 0 to b minus 1, this can be 0 to b minus 1.
Yeah.
What is it? P into P, how many times? N times, P power n, which is like it's supposed to be.
Can every element be same then?
What do you mean?
Sorry, like a not a1, an minus 1, they can all be same.
Yeah, of course it is. Yeah, they will be. All of them will be 0, all of them will be 1.
But
Make it
x, limiting n is
alright. So that's about
p
it.
minus 1 to the power n. So it's p minus 1 to the power n.
नहीं constant term कितना है?
Constant terms को p minus 1 4 to the power n. p हर एक उसका
p to the power
0 से p
तेरे साथ अच्छा
Can you hear me?
तो
Okay, everyone, can you hear me? Am I audible?
Yeah.
Great. Okay, so we'll start with the cryptography part of it now. So, so you would have all heard that cryptography allows you to secretly communicate messages, etc., etc. You've heard stuff about the imitation game and all of that. But cryptography has been used historically to convey secret messages. But what I want you to keep in mind, one prototypical example I want you to keep in mind for modern cryptography is the following challenging problem. And you'll see all forms of classical historic cryptography is much easier than this. So the problem is as follows, and this is something we do every day, it's a problem we face every day. Say, there is a laptop here in India, and this guy wants to communicate over some chat channel to another laptop which is sitting in London, right? So any messages that go from here to London, this laptop L1 to this London laptop L2, goes over the public internet. And the thing with the public internet, everyone can read whatever communication is going on in there. In particular, the messages hop from one node to one server, etc., etc. So people can read your messages. So you somehow want to hide the information. So you say, okay, we'll encrypt and send it. But here's the challenge. This laptop L1 and this laptop L2 have never communicated before. They just found each other online and have never communicated before. So they can't set up. If you look at the classical encryption schemes, you'll see there's something called a secret key which two people agree on. But these people have never communicated before. There's no way they could agree on a secret key beforehand. And if you say okay, L1 can just generate a secret and just send it over to L2 over the public internet, then everyone is able to read that secret anyway. So they can use the same thing to, they can just copy whatever L2 is doing. In particular, to put it into perspective with an example here, so I'm over here, and anyone who wants to volunteer as an example? I'm not going to call you on stage, don't worry. I'm just going to use your shirt for that.
This was black. This was black.
Yeah, okay. So, this gentleman in the black t-shirt over here, I don't know his name. I'm going to assume he also doesn't know my name, and that we have never met before. Say, I want to have a conversation with him such that only he and I understands what we are talking, and even though all of you can literally hear us, so I'm not going to whisper in his ear, I'm going to stand here and talk to him. Is there any way for me to converse with him in such a way such that even though we have never interacted before, and all of you can hear us, we are able to converse with only the two of us understanding everything we're speaking and none of you else having any clue about what exactly we are talking about. This is what modern encryption allows you to do. All classical encryptions have, always assume that two people have met before and they have a secret, but I have never met him, he's never met me. How can I still do this? This is a challenge we will address, not in this talk though. This will require the next week for us to reach there, but we'll build up to next week with that. But this is one problem we will address. So let's start with the historic ciphers and we'll see how math comes into the picture. So where is the pen?
If you two guys have never communicated before, then there is, according to, then there is nothing which differentiates him from the rest of us. So how do you,
So visually I can see him there. Online you can have an identifier, and each person can have a unique identifier. So the thing that, because I want to talk to this person who has this unique identifier, that's the notion of an identity.
I think he means that the prior information is the same. Like what information he has, even he has that. So you can't communicate anything to him without him understanding that.
No, I can. That's exactly what cryptography allows you to do. So I can identify him and I can distinguish him from him. As long as I have an identifier for him. Now what you said is true. Any information he has about me, even he has about me. But even then, I want to be able to communicate with him in such a way such that only he and I can understand and he cannot. So this looks very paradoxical, this looks very magical, but you will see, especially if you come here again next week, you will see that cryptography in fact allows you to enable this magic. In fact, a lot of things in cryptography they do it, and you will actually understand how.
I think the question he's asking is, if I impersonate as him, can I steal your messages? Can I impersonate as him in some way and steal the messages?
No, I mean, so I'm saying I'm talking to this person with a unique identifier. now, of course, you can always say, if I can link him to a real person, and
If I copy his identifier, say, can I kind of impersonate him and
yeah, that can also be done. And the way that is solved is using something called digital signatures. So signature is something only one particular person can generate, and we'll actually cover that next week. And again, getting there will take a little bit of time, particularly this week's. Anyway, okay, so historically, ciphers, the earliest known ciphers were okay, one of the more famous earliest known cipher was the Caesar cipher. So this was used by Julius Caesar during warfare, and all it did was very simple. You have the English alphabet, you take any letter, and to encrypt, what you do is you shift every letter by 3 to the right. So if I want to say, apple, I will instead send A plus 3 is B, C, D, P plus 3 is S, right? I think this is S, this is O, and this is H. This is my encryption, and how do you decrypt? Shift back to 3. Okay, question. Where does Y go to? What is Y plus 2?
A, B.
B. Yeah, so after Z, you just return back to A. So, you can think of A to Z being written on a circle, in a sense. So instead of, Caesar used a shift of 3. Alternatively, you can use a shift of K, where it can be 4, 5 or whatever. And this is called a Caesar cipher. So here, the plain text is what you're encrypting. The key is the shift K. And then the ciphertext is, shifting the message by K to the right. Why is this insecure? If I give you a Caesar encrypted ciphertext and I don't give you the key, how will you crack it? Just brute force all possible values of keys and you're done. I mean, only one of them will make intelligible sense with forming these sentences. That's why this is a very weak cipher. But one way you can represent this mathematically is essentially what you're doing is, if for instance assume that you represent A by 0, B by 1, Z by 25, then this encryption decryption is mod 26 arithmetic, right? Encryption is addition mod 26, decryption is subtraction mod 26 by 0. So this is clearly bad. There is also one example, another classical example is called an aatwz cipher, which is not even a cipher technically because there's no key in it. What happens is A maps to Z and Z maps back to A, B maps to Y and Y maps back to B, etc. And if any of you have read Dan Brown's second novel, this is called the Da Vinci Code, you would have seen this. If any of you have read Digital Fortress, trust me, I love Susan Fletcher, but the cryptography in it is pure hokum. Especially there's some weird theorem he mentions that does not exist, and that theorem is proved to be provably wrong. So, historic fiction. Okay, so this is called the Caesar cipher, and this is the aatwz cipher. So something slightly better and slightly harder, and this is something you can explore on how you can crack is Vigenère cipher. So Vigenère cipher is a little smart about things. So say you have a message, okay? So this time, your key would no longer be just a single number, it will be a word. So say my key is, I don't know, was, W-A-S. So what I'm going to do is, this is my message, and my key is was. What I'm going to do is, I'm going to keep writing was, I'm going to keep repeating WAS for whatever the length of the message is. Yeah. And then I'm going to add them. So again, A is 0, B is whatever, and then you add correspondingly. I'm not good at addition, I don't know what the value of I plus W would be, but whatever, you get stuff like this. So you kind of encrypt by adding, again, the corresponding letter values, and how you decrypt, you subtract the whole thing again. So now this makes it difficult, right? Because in a way, Caesar cipher is Vigenère key length 1. Right, you're just quote unquote encrypting by a shift, you can map that to a letter. But Vigenère, you're actually taking a key that is like a word and then you're adding words per se. So now, if you give your Vigenère encrypted ciphertext, your first issue is going to be the fact you don't even know the length of the key. And even if you know the length of the key, if I say the length of the key is say 20, then you have 26 to the power 20 possible keys. So even knowing the length of the key, brute forcing is hard. So how do you crack it? Turns out there are very interesting statistical attacks on it, and our topic is modern cryptography, so I will not go into the statistical attacks per se, but this is an interesting homework problem to figure out how Vigenère is determined. Because Vigenère was thought to be uncrackable for around like 2 centuries. It was called the Ciphers in decipherable, my French is bad, but called which translates to the undecipherable cipher, but it was cracked, and it's cracked badly. Today you can find ignorance almost everywhere. And the last classical cipher we will come to before actually starting with modern cryptography is the monoalphabetic substitution cipher. So what monoalphabetic substitution cipher does is that let A be the English alphabet, and so you consider a bijective map from the English alphabet. So you consider permutation of the English alphabet, right? So you have any permutation of the English alphabet. So say you know that I'll make the first 5 rows of it. Say A goes to B, B goes to X, C goes to D, D goes to R, E goes to D. So you have some permutation like this, right? So each letter goes to some other letter. It's a bijective mapping. What you do is whenever you have a message, you replace each letter in the message by its corresponding image in the permutation. That's the encryption. What is the decryption? You take each letter in the ciphertext and you map it back to its free image in the permutation. So how?
Here it will be 26 to the power 26. The number
26 factorial.
Okay.
So the key is basically the permutation. And so how many keys do you have? It's 26 factorial, right? You have 26 from JE math or whatever. Yeah. So 26 factorial turns out to be a very large number. In fact, it's so large a number that modern computers would struggle to brute force it. Some supercomputers would too. So it looks like monoalphabetic substitution cipher is very safe, right? I mean, it has insanely huge key size. But no. So monoalphabetic substitution is also again very easily broken. You will find like thousands of internet websites that break it for you. And the whole idea behind it, in short, is something called frequency analysis. And the frequency analysis for this is actually easier than that for Vigenère. So here's the thing. All of you would have heard of this interesting fact that in the English language, E is the most common letter. You take a large passage of text and you look at what the most common letter, it will turn out to be E. So, if E is the most common letter in the English language, then in a monoalphabetic substitution encrypted ciphertext, you find whatever the most common letter is, that should be the encryption of E. Turns out the second most common letter is T. So you find out what the second most common letter in the ciphertext is, that should be the encryption of T. And with this, now you have slowly recovered a little bit of the key. And you can continue doing this, then you can look at bigrams, which are like 2 consecutive letters which occur frequently together. And if it's like a word and you see like an isolated single letter word, it's either going to be the encryption of I or A, because we don't really have any other single letter word in the English language. And with this, you can easily recover the original ciphertext. In fact, you find these games on the Play Store and App Store where you crack monoalphabetic substitution ciphers. In some newspapers also they give it. So even though the key size is huge, it's broken. So just because you have a large key size, that does not mean your cipher is secure. So that's a small primer on classical cryptography. But now we come to modern cryptography. So when we come to modern cryptography,
but it is not necessary that even in the particular passage T is the second most common letter.
It's not. But with good probability it would be. And it is possible even. So first of all, you have a large enough ciphertext, with overwhelming probability T will be the most frequent. But if it's small enough, T might not be the case. And instead, you can guess it around a bit, and maybe it would be A then. So it's for digital. It's made for the digital world, and digital world is ruled by bits. Right? That's why we needed to cover what bit strings and so on. So the first form of encryption in digital cryptography, in fact, is a method which also offers a perfect secrecy. And perfect secrecy means it's like mathematically secure. There is nothing you can do to ever crack a perfectly secure cipher. So all of you who've read Digital Fortress there is some weird fake theorem he Damron mentions which says that no cipher is perfectly secure. I mean, there is a cipher which is mathematically perfectly secure, and that's how you come in here. I still have Susan catch with it. Yeah. Anyway, so this perfectly secure cipher is called the Burnham cipher, or more frequently known as the one-time pad. And this is how it works. Okay? So your messages are all going to be bit strings now. So say this is your message. 011. And what your key is going to be, your key is also going to be a randomly generated bit string of the same length as the message. The key is going to be a randomly, it has to be chosen uniformly at random from all possible. So say the length of the message is n. So your key has to be a bit string chosen uniformly at random from the set of all n length bit strings. So say my key is
One second. How does the computer generate randomly? Because there has to be some algorithm.
That's a question I will come to soon. But yes, that is a problem. How you generate keys randomly, and in fact, turns out it's very difficult to do that. And we come up with something called pseudo-random generators instead. But there are issues even with that. But that's an excellent question. How do you mathematically you just assume it generates something randomly? How does a computer do that? Because a computer can only follow deterministic operations, and that is to this day one of the challenging questions in computer science. Because just assume we somehow have a way of generating random or at least random looking numbers. So now we have a message and a key, and a message can be anything. So you can study this in computer science. You have an image, you have a music file, you have anything, you can always represent it in binary. So now the way you encrypt it is you just use XOR the two things. So the ciphertext is going to be M XOR K. So let's quickly go over this. This is your ciphertext. How will you, knowing the key and the ciphertext, how do you decrypt it?
You get the random generated key. If you get the random generated key again, you can predict the message.
Yes. So you want to quote unquote subtract the key, but in mod arithmetic, addition and subtraction are the same thing in a sense. Right? So you XOR it back again with the key. So 1 0 1 1 0 1 1 0, and then you get like 0 1 1 0 0 1 0. You get back the message. This is called a one-time pad for a very good reason. It's that you can use a key to generate to encrypt a message only once. In particular, you can't use the same key to generate two different messages. If you do, then your scheme is no longer secure. And this, by the way, this blunder has happened in history. So back during World War I or World War II, I don't remember, Russians were using one-time pads. And it's hard to generate keys, right? Because your key needs to be as long as the message. So they're like, you know what? Instead of regenerating keys, we'll just repeat the same key again. So they instead did one-time pad encryption, but by reusing the key. And the US intelligence figured this out, and they could actually take the repeated key usage, and with that they are able to decrypt the Russians' messages without knowing the key, just because they reused the same one-time pad. This project was actually called Project Verona. You can search it up. And this tells you have to be very careful with cryptography. If someone says a key is meant for one-time use, it's meant for one-time use. You can use it twice, but then all security guarantees are off. But if you have one-time pad, then it looks like we are happy, right? Our problems are solved. We've got a perfectly secure mode of encryption. What's the issue with it? Can anyone tell me what could be an issue with it?
Communicating the new key each time to both ends. Communicating new key each time could be an issue.
Yeah, so communicating a new key each time could be an issue. Exactly. And this is the exact problem Russians faced, right? Which is why they decided, oh, you know what, we'll just reuse the key. And that is a problem. The key length will be equal to the message length. Exactly. So if you have a very convenient, easy way to secretly communicate the key, just use the same thing for the message, since the key length is the same as the message anyway. Right. So you don't really have. So the only way for this to make sense is, if like I send you a very long key on a strip via parcel and all of that, which is also what the Russians did back then, except they decided to repeat the same strip. So In fact, this is a theorem called Shannon's theorem, which says that for any perfectly secure cipher, the cardinality of the key space has to be greater than or equal to the cardinality of the message space. In particular, if you have a length function, the length of the key has to be greater than or equal to the length of the message for a perfectly secure cipher. And this is the problem. Like,
But what if I understand what happens when the length of the message is equal to the length of the key. What if the key length is greater? What happens then?
I mean, you can have systems where the key length is greater. It's just that it's longer than the length of the message now.
So some part of the key is ignored.
Sometimes you can ignore some part of the key, and you can, so something you can quote unquote, so if this is your one-time pad key, something like this where it just repeat everything twice is also a valid one-time pad key. Now, I mean, it makes no sense for you to go for this instead of this, but what the theorem says is, so in essence, there is theoretically no problem if you go for a longer key. Practically, it doesn't make sense to do that, but theoretically, there is not an issue, right? That's what the theorem says, it has to be greater than equal to for perfect security. But yeah, so now what we actually do is, we don't want mathematical security. The relaxation is we go for something called computational security. In particular, as long as I think of it in this way, as long as I have like a bunch of supercomputers, from each atom in the universe I put a supercomputer, and I let them run for like 10 billion times the age of the universe. Even after all that, they should not be able to, crack my encryption with a probability greater than 10 to the minus 200. So extreme assumptions, but essentially, mathematically, you can quote-unquote crack my cipher with like completely infinite computational power, but with any reasonable amount of computational power, you won't be able to. In fact, even with an unreasonable amount of computational power, such as supercomputer at every atom, yada yada, whatever I just said, you won't be able to. So that is what we relax our requirements to computational security. And with that, we start modeling cryptography. And I'm going to cover two things today. There's going to be something called stream cipher and a block cipher. And the way the stream ciphers work is, the one-time pad was nice. You have a key which is as long as the message and you solve with it. But can I do something in the form key where I have a much shorter key and I somehow plug that into a function, and then that short key becomes a long key as long as I want it to be. So this is called a pseudo-random number generator. We have the notion of pseudo-random number generator. So what a pseudo-random number generator does is that it takes in a small seed S, so you feed it S, and it outputs numbers. In particular, for now for simplicity, it outputs an infinite list sequence of numbers, such that if I know S, then of course the whole thing is a deterministic algorithm. But if I don't know S, each of these look random to me. In the sense that even if I know some prefix of it like this, I should not be able to predict what the next number is going to be. In fact, we have a stronger requirement that if I know any subset of the output, I should not be able to figure out anything about the other.
But if we know the full output, if we have the full output, we can figure out the S part.
Full output because it's infinite.
Okay.
But something like, say you have x0, x1, x2, x3, x4. Say even if I know x0, x1 and x4, I should not be able to figure out what x2, x3 is. I mean, I can always guess, right? But I should not be able to do any better than guessing reasoning. So, do PRGs exist, first of all? That's the first question, right? It's still an unanswered, open problem. We do not know. I mean, if you can prove that P not equal to P equal to NP, then they don't exist. If P is not equal to NP, then they can exist. And P equal to NP is, by the way, the classic millennium prize problems. It's unsolved. Computer scientists and mathematicians have broken their heads over it for years. No one knows. So essentially, yeah, we don't mathematically know if PRGs actually exist or not. But we have some fairly strong candidates in the sense they look random to us and no one has been able to crack them. So, one bad example of what a pseudo-random number generator is is something called the linear congruential generator. And here we are going to do maths, and here we are going to break the system too. So you people are going to help me break the system. So this LCG is actually used by C, Python. Slight variant of it. But C, Python do use it to generate random numbers. So now here's the thing, in general, for your general purposes, whenever you're using random number generators from C, Python, C++, etc., you just want nice statistical properties, and their .rand function satisfy it. But for cryptography, you need like secure random number generators in the sense that they should be unpredictable. So one of the mistakes people do in implementation cryptography is they use the C, Python normal rand function, and that screws up because you can actually crack that, and we'll actually go through how you can crack the C, Python rand function. And that is why cryptography should not use any random number generator, you should use a cryptography secure random number generator. This is how the linear congruential generator works. So linear congruential generators has three parameters, A, B, and N. These are all positive integers, where GCD of A and N is equals to 1, and of course like A comma B is less than N. You will see why one is this. These are all non-negative integers. So here's the thing. So this is how it generates. So say your C is S, right? So your first value output is going to be AS plus B mod N. Your second output is going to be AX naught plus B mod N. The third output is going to be AX1 plus B mod N. So on and so forth. You can see the rest of the pattern, right? Now, why is it insecure? So we'll consider three cases. We'll consider the case where, okay, so you can see the output, right? So if it's secure, seeing some portion of the output, you should not be able to figure out the rest of it. So A, B, and N are public parameters for now. Assume we know all three of them. Then how can we crack it? So say you have seen X naught, you know the values of A, B, and N. How will you predict the rest of the numbers?
Put in the values.
Just generally put in the values.
Even if we don't know A, B, and N, we can figure out by 3 or 4.
Yeah. We'll do that. We'll actually start, just to show how terrible this is, we are going to start relaxing how much we know and still see we can figure everything out. So by the way, in C, Python, you know the values of A, B, and N already. So literally given just one output, you can figure everything out. It's that bad. It's actually a little bit because there also be some kind of condition, but even that can get that. So clearly this is a terrible thing. Okay, so now someone comes up with a bright idea and says, you know what? I'm going to hide B. So I don't know what, yes.
This is like generally Python, C++, and C always use this algorithm to generate numbers.
Yeah, so it uses a variant of this algorithm where we also drop a few bits. So it's called a linear congruential generator with truncation. But so one way to attack that is using something called lattices, which we'll cover briefly. But
what's the benefits of using this? Like why does C++, why do C++?
It has very good statistical properties. Like you want it, if you're generating random bits, you want stuff like probability of 0 is probability of 1. Probability of 2 consecutive zeros is 1/4. Probability of 2 like a 0, 1 should be 1/4. So those kind of, it has those nice statistical properties.
So let's say if I say to Python, give me a random number from 0 to 10.
Mm-hmm.
It will give each number with a probability of 1 by 10 if we go for an infinite amount of.
Yes.
Okay.
So it has very nice statistical properties, and that's it. This suffices for all your machine learning and all the work. Yeah, because you just need stuff with good statistical properties. You don't care about whether they're deterministic as long as they have good statistical properties. Probably we need more than good statistical properties. We need unpredictability, which these don't have. Okay, so now say someone comes and says, you know what, I'm going to hide B from you. How would we, can we find the value of B?
How would we hide B first of all?
They just say, I'm not going to tell you what the value. I'm telling B. I'm telling you the value of A, I'm telling you the value of N, I'm not telling you the value of B. So can you still use the outputs to figure out what B can be?
Use B.
B is smaller than N, so you can analyze N minus 1.
Yeah, you can brute force, but there's a simpler thing to do.
If we know 2 consecutive bits, then we can do that.
Yeah, you know all the outputs. You know all the output values.
We got only 2 or 3 because you know the equation basically. So we can just take from the 2.
Yeah, so you don't know the series, but so you can start with, you know x0, you know x1.
Yeah.
So you can see that b is equals to x1 minus ax0 mod n. So, you know x0, you know x1, you have b already. So someone hiding b from you is not really hindering you from breaking it either. Now someone says, okay, you know what? Does this have an eraser?
Yeah, use your hand.
Just use your hand.
Yeah. So someone says, you know what? I want to hide A also from you. Not that I'm going to hide just A. I'm going to hide both A and B from you. So now this won't work because I don't know the value of A. But then even in the end, you can still break it.
Yeah,
So
right.
can anyone tell me how they might break it?
More equations.
More equations.
More equations, exactly. So let's take x2 minus x1. What is x2 minus x1? That is
Ax1
A times x1 minus x0.
And you get A.
Right?
And you get A.
So A will be x2 minus x1 times x1 minus x0 inverse mod n. One slight issue with this, this one small issue.
x1 cannot be equal to x0. If x1 is equal to x0, computer won't be able to
Yeah. In fact, it's a general problem. The general problem is x1 minus x0 might not be invertible mod n. So you see, for a number to have an inverse mod n, it needs to be coprime to n. So if this is not coprime to n, then you won't be able to compute an inverse. In that case, you continue on. So taking x2 minus x1, you take x3 minus x2. Eventually, one of the differences will be coprime to n. I mean, we did say it is good statistical properties.
Even if we can't, we know only one case, right, where it's not a coprime, so we can just do that directly. We just put that during decryption. We can put that as a case, like if it can't decrypt it using this method, A is equal to x2 minus x1 by x2 minus x0. Can't we just directly put that case as a redundancy that x1 is equal to x0 and use another?
So see, if x1 is equal to x0, then the whole thing is not even random, because then x2 will also be equal to x1. So that is unlikely to happen. What will likely happen is that x1 minus x0 is not 0, but it's just an invertible mod n because it's not coprime to n. In that case, you take x3 minus x2, that will be A times x2 minus x1, and hopefully x2 minus x1 will at least be coprime to mod n you can invert. Eventually, you will be able to invert it. Because I mean, it does have good statistical properties, and you can show that eventually you will. Now here comes the biggest challenge of all, and this is a little complex. I will hide even n from you. I'm hiding A, I'm hiding B, I'm hiding n. And this is a good math problem which you can I mean, I will outline a solution to you, and there is one theorem which I will state. But after that, the proof of it is an interesting math discussion you can do on the group. And does it not have? Yeah, it does. Okay. So this is our second last section. After this, we do block cycle and call it a day. But yeah, when I don't know A, I don't know B, and I don't know N. I don't know what the motives.
Take a lot of exercise and take their average, then double.
Yeah, but that will not always work out.
Not always work out, but it will give.
In many situations, it might. If you choose your A and B intelligently, you can make sure that doesn't happen.
No, but you said that this linear congruential sequence has good statistical properties.
Yeah, it has good statistical properties, and
so it is evenly spread out.
Yeah, it will be evenly spread out if you have like a very long.
Essentially infinity.
Very long. Yeah, of course, if you take like as the length of the thing tends to infinity, you can just pick up the maximum number and add 1 to it, and that will give you n. But the thing is, can you do it with a little? Yeah, I mean that works actually. That works. Yes. Let me rephrase it. Can you do it a little bit better by not having to take infinitely long, almost infinitely long states, right? I mean, you can always just take like 10,000 states, take the largest, add 1, and check if it works out. But the thing is, even, yeah, you can do that, but can we do it in short? And here's a very neat mathematical term. So let's write it. Okay? So I want to write that x1 is equals to, forget the c, we anyway don't know the c. So then let's start with here. X2 is and then model everywhere. So now let us look at the differences, right? This is something we did before. So say that D1 is equals to x2 minus x1. And what is this? This is nothing but a x1 minus x0, right? D0 is again x1 minus x0, of course. Yeah. And this is equals to a D0, right? D2 is, let's say, x3 minus x2, which is
X square D.
a, what is x2 minus x2? x2 minus x1, which is nothing but a D1. So in particular, d n plus 1 will be a dn, right? Everyone can see that?
Yeah, it's a geometric
Great.
progression.
And you can calculate the values of d0, d1, d2, d3 because you know the
X1,
x's.
X1, yeah.
Great. And we don't know the value of a though, but okay. Okay, all of this is of course model. All of this is model.
Right, element.
Okay, I just have one small question just to see everyone is on board. So I know d1, I know d0. Why can't I just calculate it as d1 into d0 inverse?
Because we don't know n.
We don't know it. Take an inverse, you need to know the value, and we don't even know that. Yeah. In fact, that's what we did last time when we did know, and that's exactly what we did. That we took d0 inverse. Okay. This is the trick we're now going to do. So you consider this thing where I will now define t0 to be. So essentially, my thing is I want to get rid of this a dependence somehow. So let's see what it is. Let's say I take d2 d0 minus d1 squared. Right. What is d2 d0 minus d1 squared going to be? It is going to be like a d0 a squared d0 squared minus a d0 whole squared. Right? So this is congruent to 0 model. So this gives me t0, which is congruent to 0 model. Similarly, I define t1 to be d3 d1 minus d2 squared, where that will be congruent to 0 model. So effectively, I have t1, t2, t3 dot dot dot, and I know these values, and they are all congruent to 0 model. In particular, they are all multiples of n, right? And if they are all multiples of n, what I can do is I can take the GCD. Right. So we can take like we can take it t4 also and calculate the GCD. And with high probability, this will actually turn out to be n.
Here it is not deterministic actually, because there can be like after like t n plus something, n tends to infinity, there can be a value which will return higher GCD than the terms before that.
No, the GCD cannot increase as you add more things, right? So if you have like GCD of a1 dot of a n minus 1, that can only be like greater than or equal to GCD of a1 comma a2 comma dot of an. Like if you add more things, the GCD can only ever decrease.
Okay.
Because it has to be a common factor of all of this, and then it needs to divide that. It's not able to divide that, the GCD will decrease. GCD will never increase. Yeah. And turns out with high probability, n will turn out to be the GCD of all of them. And in fact, this is something I'm not going to prove, but the whole idea is if you have k positive integers selected randomly, then the probability that the GCD is 1 is given by 1 by zeta k, where zeta is the Riemann zeta function. You would have heard of the Riemann hypothesis that actually knows the zeta function, and then zeta function makes an appearance. In particular, if you take two random numbers and you want the GCD to be 1, the probability of that is 1 by zeta of 2, and that is actually 6 by pi squared. It's something less than 1. I don't know the example. You can calculate it and check. But yeah, I mean zeta, it's itself,
Why do you say here that?
it kind of has an exponential growth. So the more you take, the probability of it being the GCD of them being one exponentially, in a sense, exponentially increases. In a sense, exponentially. With very strong this thing of exponentially increase, because I mean you can never cross
the last part.
So the growth of this error probability, let's just say that the GCD of k things will not be 1, the error probability decreases exponentially.
Okay.
Relatively.
That's why you're saying high probability.
So with high probability, you'll be able to recover it in a very short number of.
How was TA defined here?
So this
General, like what will
dn will be dn plus 2 times cpn minus dn plus 1. So now that we have all of this now, so here is how PRG works. Sorry, a stream cipher works. So what the stream cipher does is that it takes a short seed, you feed it to a random number generator, and that will make it into a long bit string with length, whatever you want the length to be. You have your message, and you just generate enough of the random number generator output to match the length of the message, and then just like you want and you solve it. And the key is just the seed, and the seed can be short, right? With a short seed, you can generate an infinitely long key. And with this, you can actually use you and I are talking, we can use the same key to communicate multiple times, as long as we take the next part of the sequence. We shouldn't just repeat from the start. So if you and I are talking, we know the messages to send before we know that previous message means we can continue. That's how a stream cipher works. And the last thing I will talk about in like 2 minutes, because there's no point going into the internals of this, but the internals of this is what requires finite field arithmetic, prime extension fields and all of that, is something called block cipher. So the way a block cipher, so AES is an example of a block cipher, which is used in this example. So the US set up this competition to decide advanced encryption standard, and there's a guy named Rindale, his cipher worked, so the Rindale cipher is also known as the AES now. And how block cipher works is simple. You basically have a block, you have something, you have a 16-byte message. The message has to be 16 bytes, and there is a key, right? So what this block cipher does, it takes the key as input, it takes the message as output, and it gives you a ciphertext, 16-byte ciphertext as output. So the whole idea is, given one particular key, this block cipher acts as a permutation. And for 2 different keys, it will produce 2 different permutations. And the whole idea is, if you don't know the key, it is hard to figure out all the permutations. So decryption is also efficient in the sense, if you know the key, the inverse permutation is also easy to compute. That is how block ciphers work, and then here's a question which you can ask me later on, try finding out. So this is a 16-byte messages, right? What if I have like longer messages? So I need to, you can't extend the length of the block cipher. Your block cipher will only take like 16-byte messages. It doesn't have 32-byte messages. So how do you extend it to 16-byte?
Use the same key, but in multiple blocks.
Yes. So one way to do it, and then how to do it is that I have a 32-byte message. What I will do is I just send this over here, and introducing block cipher. In fact, this is something called the electronic code book method. The reason this is bad is it leaks information about the message. In the sense, if my block 1 and block 2 are the same, then my ciphertext block 1 and ciphertext block 2 will also be the same. So as an attacker, just by seeing the ciphertext, I can still tell you that the 2 blocks of the message are equal, which is bad. I don't want any information about the message to leak. So ECB is a very bad example. And then if you go to Wikipedia and type ECB, you see this image where like a penguin is encrypted under ECB, and then you can see that the penguin's pixels do get encrypted, but you can still see the shape of the penguin. So it's a very bad, way of combining these block ciphers. There's another way called CBC, cipher block chaining, and that is something I cannot go into due to the interest of time, but you can look it up, and that is something that solves this issue of how you chain things. CSeC is not the only way, there are also other ways, but CSeC is the most used. And with that, we'll call it a day for the cryptography part of this talk. If you want to see how all this is implemented in code, hang around and you will see a whole assignment. Not assignment, you will see a notebook where things are implemented, you can code around, you can ask, and it will be nice homework for those of you who are programming that will plan to implement some of these things, tinker around with it, and see whatever crackings we did, the things we cracked, if you can implement that program. With that, I will hand over the mic to Harsh.